Hello. In this video, we are going to discuss the concept of conjugate acid-base pairs. So as you already know from previous videos, we are discussing Bronsted-Lowry acids and bases. So if you remember, a Bronsted-Lowry acid is a proton donor. And so to fulfill that, the criteria to be a proton donor, one or more ionizable covalently bond hydrogen atoms in your structure. A Bronsted-Lowry base, on the other hand, is a proton acceptor. Okay, is a proton acceptor. And so to meet that criteria, you have to have a lone pair, a lone electron pair in your structure able to catch the H+. So I like to think of species as I'm very bad at art here. Okay. I'm open. So think of Bronsted-Lowry bases as like people with their hands free. Think of each arm as these hands as the lone electron pair, ready to catch the ball, which is our H+. Okay? And so a Bronsted-Lowry acid, so there's base acid, has the ball and is holding on to it. Okay? Has the ball and is holding on to it. So this represents our 2-electron covalent bond. And the open hands represent our lone electron pair, which again is 2 electrons, right? And so a proton transfer is a game of catch. Okay? So, what are conjugate acid-base pairs? Well, let's say I've got some acid, HA, right? So I've got the guy holding on to the ball. And I ask, so this is our Bronsted-Lowry acid, BLA. What is its conjugate Bronsted-Lowry base form? Okay, what is its conjugate Bronsted-Lowry base form? Well, to turn a Bronsted-Lowry acid into a base, we need to remove an H+. Okay? Now note what that does. Removing an H+ decreases the number of hydrogen atoms by 1 and decreases the charge by 1 because it's losing an H+. So if we take HA, which is neutral, okay, I'll put a little 0 there to say it's neutral, and we remove the proton from it, we're left with A-. Okay, so A- is the conjugate base of HA. Okay, so if you want to see what something looks like as a conjugate base, you got to take an H+ away from it, and which turns it into a base, right? That's what turns it into a base. Remember, the 2 electrons in this bond are what become the 2-electron lone pair to again receive the ball. Okay? Now, if we go the other direction, if I take HA here and I ask you, get rid of that too. To show me what HA would look like as a conjugate Bronsted-Lowry acid, well, we're going to add H plus to it. And so note, adding an H plus increases the number of hydrogen atoms in the structure or in the formula by 1 and increases the charge by 1. Okay? Now, this could only occur, by the way, so let's say we have our HA here, if A here has a lone electron pair on it. So it's covalently bound to a hydrogen, but it has another lone pair free to accept another proton, right? So if we add a proton to this, we increase the hydrogen count by 1, so it becomes H2A, and we increase the charge by 1. So it goes from 0 up to plus 1. So H2A would be the conjugate acid of HA. That is the conjugate acid of HA. This is the conjugate base of HA. So if we ask for conjugate base, you take whatever the formula is, you remove one of the hydrogens, and you decrease the charge of the overall species by 1, making it more negative or less positive. If we want to turn it into a conjugate acid, we add a proton to it, right? Now note, there are certain things that can and cannot be conjugate acids and bases. Let's look at a scenario here, okay? Let's look at H2CO3, HCO3 minus, and CO3 2 minus. So you'll note, going in this direction, we are losing a proton, okay? We're losing a proton going in that direction, and then going in this direction, we are gaining a proton. Okay, that means going from left to right, starting from H2CO3, that means that HCO3 here is the conjugate base of H2CO3. Because the conjugate base, we remove a proton to do that, okay? Okay, so now we can see that, oh, actually here, we do it on the other side of it. Okay. This is the conjugate base of H2CO3, and that means that CO3 2 minus is the conjugate base of HCO3 minus. Because going from HCO3 minus to CO3 2 minus is another removal of a proton. Going in the other direction, HCO3 minus, if we start with CO3 2 minus and we add a proton to it, okay, this then is the conjugate acid form of CO3 2 minus. Because if you take CO3 2 minus and you add a proton to it, that's what it would look like as an acid, meaning that the CO3 2 minus form of it is its base form. Okay, and then again, if we add another proton to HCO3 minus, HCO3 minus is the conjugate acid form of HCO3 minus. Okay, so what that means, and so this is a good example of this, this is what we call a conjugate acid-base pair. H2CO3 is the conjugate acid form of HCO3 minus, and HCO3 minus is the conjugate base form of H2CO3, right? And we could do the same thing over here, okay? HCO3 minus is the conjugate acid form of CO3 2 minus, And CO3 2- is the conjugate base form of HCO3, right? Now note, there are limits to this. You can't infinitely add like so. For example, let's say we start with CO3 2- and we want to see what is the conjugate base form of CO3 2-. And so we would try to remove another proton, and we find that it's not possible because CO3 2- doesn't have any ionizable protons. So there are no protons to remove to see what, because that would mean that CO3 2- is the acid form. So to see its conjugate base form, so that means that there is no conjugate base of CO3 2- because there's no H atoms in the structure. It doesn't meet the criteria for it. If we go to the other side, right, and we ask, well, then what is the conjugate acid form of H2CO3? Well, we could draw the Lewis dot structure here, and you're not going to have to do that very often, but it is useful. Oops, I drew that wrong. Give me a moment here. Yeah, there we go. I'll draw it like this. So there's our H2CO3. And as you can see, there are lone pairs here. We can add a proton to this, forming, theoretically, H3CO3 plus. Okay? So this species would be, if it existed, the conjugate acid form of H2CO3. So you'll note that the term acid and the term base are relative. And it depends on the behavior of that species in it depends on the behavior of the species and on the environment that species is in. Okay, so H2CO3 normally is in environments where it acts as an acid and converts to its conjugate base form, HCO3-, by donating a proton to something else, right? Acting as a Bronsted-Lowry acid. However, H2CO3 in most environments is not a very good Bronsted-Lowry base, and thus you don't see H3CO3 plus because most other things are so much better as a base. This will make more sense when we start to quantify the ability of Bronsted-Lowry acids to donate protons and Bronsted-Lowry bases to accept protons. Okay. Now, the last thing to note here is that for any acid-base reaction here, for any proton transfer, whatever your Bronsted-Lowry acid and your Bronsted-Lowry base are, they turn into their conjugate form in the process. So HA, which is a Bronsted-Lowry acid, becomes its conjugate base form A- because it lost the proton, and thus B, our Bronsted-Lowry base, in accepting a proton, becomes its conjugate acid form. So proton transfers are two conjugate acid base pairs. Okay, so whenever you have a proton transfer, you have one thing converting to its conjugate base. You have the acid converting to its conjugate base form and the base converting to its conjugate acid form. So that's sort of why we need to have these terminologies. Okay, and the way you identify this, just really simply, let's do one quick example here. Let's say I have H2S plus NH3 forming HS minus plus NH4 plus. Okay, and so here, let's try to identify which one is which one's the acid, which one's the base, which one's the conjugate acid, and which one's the conjugate base. So if we look here, you can see here for the NH3 to the NH4 plus, it is gaining an H plus, right? And the charge is going up by 1. So it is gaining a proton. Okay, it's gaining a proton. And so what things gain protons? Bases, right? So this is our Bronsted-Lowry base. Okay, and that means it's becoming its conjugate acid form. It's Bronsted-Lowry conjugate acid form. So that means that our H2S is losing a proton from the reactant side to the product side, meaning that our H2S is our original proton donor and thus is the Bronsted-Lowry acid. And in donating its proton, so donor, acceptor, it becomes its Bronsted-Lowry conjugate base form. So that means H2S and HS minus are a conjugate acid base pair where H2S is the acid form and HS minus is the base form, right? NH3 and NH4 plus are a conjugate acid base pair where NH3 is the base form and NH4 plus is its acid form. Later, we will talk about which one is the better acid and which one is the best base. Because we're going to find out this is what we're talking about. This is how come things can, sometimes they can act as acids, sometimes they act as bases. It depends on what else is present. If something else is better at giving up protons than you are, and you have a lone pair, you're not going to get to donate your proton. You're going to have to accept their proton. Okay? So that concludes our discussion of conjugate acid-base